3? Yes.
Just indium-3. Okay, cerium indium-3 structures.
Okay, thank you very much. It's really hard to see from here. I guess I may stay here. Yeah, thanks for the introduction, and thanks for this the invitation for me to be here and talk to my recent work and these materials. It will be nice to talk about because I've heard just a little across this workshop about heavy fermions. I saw there's some papers, some posters over there, but during these talks here, I think I'm gonna be talking more about these materials and especially heavy fermions. Okay, this work's wouldn't be possible without help of many guys here, especially the postdoc, Maria Helena, this is Pasquale's postdoc, and my student, PhD student, David Zal. But all of them worked pretty hard to make this sample possible. But I would like to thank also the people from Los Alamos, Steve from Sandia Lab, the guys here from Mag Lab, where we carried out our NMR, low temperature NMR measurements, and also all the funding that supported this research here. So the outline of my talk is here, just in a summary of that. I'm trying to convince you why we need to look at this cerium indium-3 in a different morphology, and I'm gonna say and try to present some motivation about that. And also talk about the method to grow these materials in this kind of morphology. That's a new technique. Later, I'm gonna talk about some characterization of these cerium indium-3 nanowires. So I'm gonna present electron diffraction spectroscopy, magnetic susceptibility, specific heat. Those are the macroscopic characterization, but also I'm gonna present nuclear magnetic resonance data, and also finish with some EDS results here. And then I'm gonna say some words about a summary here. Why should we look at 1D cerium indium-3? That's really important. Those kind of nanowires, it's hard to make them, but it offers us a very good input to the physics of these materials in 1D direction. There is some appealing to quantum computing or quantum information for these guys because of its large nuclear spin and also the quadrupole moment. Some people are using that as quantum dots because through NMR or any QR, actually we can manipulate the matrix elements as a quantum bit and transfer that and transform that in quantum information. So this is some intrinsic appealing for these materials. But from the theoretical point of view, that's most important, I guess, and I will try to make my point here. The archetypal condor lattice model is difficult to solve for real materials. We know that we can solve it in 1D direction. That's actually the talk, I guess, Rodrigo talked about. But for real materials, when you have a lattice 3D, this is really hard to make. And theory actually fails. There's a lot of discrepancies when you try to look at the order, magnetic order, and also the magnetic moment. DMFT, DFT, they always came up with a very suppressed value for this. And a sort of a spoil here. Actually, when we change this morphology, I'm going to conclude and actually try to convince you that we, just by confining the sample in a single direction, we are favoring the suppression of this. So maybe we can find a middle point here from real life or experiment and theory, and make life easier for you guys to make some calculation here. So let's say we try to make the sample now, try to adapt the real life to the theory instead of adapt the theory to the real life, and make the z direction way, way larger than the radius of the sample here. The important quantity here actually is the Fermi wave vector. So obviously we cannot make a material with a single atom chain, but I think, and maybe you guys can teach better me, but the correlation here is, or the length scale here, which is important, is the wave vector. So we can choose. I think I'm going to show you how we make these wires, but I think we can choose the radius of the wire to adapt it to this wavelength here. I don't know how much is this right now, I'm thinking about, but maybe we can get closer to that. So to start talking about CeIn3 and heavy fermions, I would like to show this plot that summarizes all superconductors, or many of them here, along the years. And CeIn3 is, like Jörg mentioned there, is a very poor metal, or is a critical superconductor in his colloquium on Wednesday. And it lies in this family of material here, these heavy fermion superconductors, and displays this kind of physics, where magnetism is on the vicinity of superconductivity with quantum criticality and all these problems here. And these family of materials are important because there is a plethora of novel quantum matter states. So unconventional superconductivity, electronic and nematic states, as already mentioned here, hidden order, and more recently, topological states of matter, Kondo insulators, and so on, and the putative chiral superconductors. So this is a really interesting phase diagram, and this is a very interesting family of materials here. So talking about CeIn3, specifically, these materials orders at room pressure or ambient pressure at 10 K. It is antiferromagnetic with this magnetic structure here. It has a 4F order moment about 0.4 μb in this plane. It's a dense Kondo compound with a gamma 130 milli-K mole Kelvin. It is superconducting at under pressure at about 25 kilobars. And also the ground state here is a gamma 7 doublet ground state from this J5 halves. So there's all these behaviors, these underlying physics going on with these materials, which makes it very interesting. So here I show you some plot that's is a bit of an idea, but is for many a bit controversial. But we can think of TC with a linear relation with the ratio between the lattice parameters, C over A. And we understand for the unconventional superconductors that the highest is this ratio, the largest we can reach TC, which is not true for BCS superconductors or conventional superconductors. So the idea in the beginning, back in the days, maybe 2000s or something, was to pick CeIn3 and stack them, trying to increase this ratio, C over A, trying to get to a larger TC or so. But instead of getting this simple picture here, what we've got was this very famous family as well, we call 115s, where M here is transition metals, so which is a very important family of environment as well. So this is not the scope of my talk here, but I'm gonna flash some slides just to show you the richness of the underlying physics we observed already for this kind of structure, and then I go back to the basics there, where we are studying now CeIn3. So as we can see in this phase diagram here, it's pretty rich. If you change M here, using cobalt, rhodium, or iridium, we can find many different ground states. Some of them superconducting, some of them magnetic. So the first one, if you look at cobalt here, I'm not going to explain in details here, but I would like to mention, because it was very important in that time, this novel phase of superconductor, the food ferrolarkin of Shinnikov, that was found in these materials way down there in temperature, millikelvin temperatures. And we also did some work on that, especially myself, I did some NMR work, and we could contribute. If you are interested in some results, you can check these papers here. But what we found here was a very inhomogeneous state or phase with field-induced magnetism. About FFLO, I don't know, we couldn't say much. Some people still claim the existence of this over there. Some people just don't believe there is something related to that. However, when we pick the samples here with a superconducting ground state and dope it, what happens is this is represented here in this phase diagram. So if you introduce electrons by introducing tin in this matrix, electron doping, just suppress tineo monotonically. However, when we introduce holes in this matrix, we can tune the system to the left side of this phase diagram, and we can reach magnetism, antiferromagnetism over there. And by that time, with quantum criticality in evidence, and all of this was a very good scenario for us to investigate the coexistence and how this magnetism was emerging over there. So NMR, again, was very nice to do here and get some input on that. We showed that in this region here, very much like in the rhodium 115s, there is coexistence of both. And if you think about this, we have only one F electron, which participates to the magnetism and also to the superconductivity, which is very interesting. Also, we could understand as far as quantum criticality works in this region of the phase diagram. And the way we explained it that actually was through a very inhomogeneous, electronically inhomogeneous scenario, where when you dope this system, you introduced an impurity, magnetic impurity, with some correlation function. So when you cool down the system, this correlation grows and eventually overlaps locally. So, and then you reach TNA with that. In a different work, we also showed that by applying pressure, we kind of suppress these correlations. However, the system, although going back to this direction in the phase diagram, never recovers the quantum criticality. So the scenario is really complicated there, and some cautions must be taken into account there. So just another example, more recent example, is what happens when you have the magnetic ground state here, introducing rhodium there. So it was reported a very novel phase here, up in there in high fields, and this has some implication with the nature of the quantum critical point over there in 50 Tesla. So we actually try to understand this sort of scenario here, doing NMR, and by measuring these materials in the hybrid system in Tallahassee, we could contribute to this scenario, providing some microscopic. That was the first microscopic evidence for this anomaly in this phase diagram here. And I should say here that this scenario found basis also for CeIn3. People in Los Alamos was investigating the nematic phase, even here and even in CeIn3 system with that. And the way we explained this by analyzing the hyperfine field here was that the wave function, the 5 halves contribution to the wave function there was getting enhanced, so you get higher or enhanced hybridization in plane, and we showed that the Fermi surface was larger over there. So, but that's not the subject of this talk here. So we should go back to basics, look at the simple material that's the basis for this whole family of materials, but using a distinct approach. So we thought we should change the morphology of these systems, like I said before, and try to help the theorists to model in a better way. Perhaps not exactly, but we find in a middle point there where we can find interesting things. What we learned with the years is that this Japanese group already did some thin films, CeIn3 thin films, and they reported suppression of magnetic order and emergence of non-Fermi liquid signatures, which means you move the system towards the right direction in this phase diagram here. But we are putting our efforts to make nanowires. So this is a challenge here. And how can we do this? How can we grow this kind of materials? And what is going to happen when we have it in our hands? So that was the subject of this presentation here. So for those that were not aware or are not aware of the physics behind these materials, I would like just to show here the Doniak phase diagram, which most likely explains the physics in these materials, with a very competition between two very important interactions, RKKY and Conde interactions. We cannot forget the crystal fields because it drives the ground state of these guys. And say some words about that, because when we change dimension, the dimension comparable to a fundamental length scale, like I mentioned in the beginning of my talk, translational symmetry rate can alter the ground state, can change this, and many body correlation effects become more pronounced. So is that we are gonna see here. So I would like to show you some pictures about how we grow these guys here. This is, as I mentioned before, is a collaboration between our group and the low temperature group in University of Campinas. It's already, we deposit a patent on this method, but the method is pretty simple. Actually, you combine a conventional metallic flux method to grow most of these materials with a alumina template like the one I'm showing here. So the trick here is how to make this template. So you can control the size of these nanopores, and you can get nanowires out of that. We follow this recipe here that's in this paper, and we create, you can control these nanopores from 75, whatever, you can choose. Okay? That is amazing that we can actually play with these nanowires here. So then you proceed as usual. Just put your material inside this quartz tube. Here you place your template inside of this quartz tube. Actually, there is a trick here. We need to open the bottle here, but then you say a little prayer, go to the oven, and hope that, yeah, that the things are gonna work well. The good thing about this method is, I'm gonna show in future slides, we can get both bulk material and nanowires inside of this. This is really nice. So just to show you some case of success here, we first grew this iron gallium nanowires. As we can see here, this is a 10 micro. These are the characterization here. We have pure iron, pure gallium inside of the wire. And we can see already change in transition, magnetic transitions compared to the bulk. So if you are interested, you can check this publication there. Another one was manganese manganese 5 silicon 3 nanowires. And this was very interesting because the nanowires not only grew inside the pore, but it kept going outside the pore. That was really nice, actually, because then we could handle it and actually perform transport measurements. Because it got out by itself, and that was really, really nice. And also there's some details here. This actually oxidize and creates some core shell structure, which was really actually interesting for the physics of these materials. A little bit closer to what were interested here is gadolinium indium-3 intermetallic nanowires. It is what I told you before. Here we have single crystals on top of the template and inside of the nanopores, and actually this was removed from the template, we got these nanowires here. And again, this was a very interesting result because, well, first we can check the phase period of these materials, gadolinium and indium. But what is interesting to us is this. Tineo was suppressed from 45 Kelvin down to 3.8, just by having this new morphology of materials here. So if you look at specific heat, also display this was interpreted as a frustration or suppression of RKKY magnetic interaction, because over here, gadolinium is an S ion, L equals 0, so it's not so complicated. But now, let's look at cerium indium-3. This was a hard time for us because it took several attempts to finally grow. It's not perfect yet. I mean, we got the correct phase, 1 to 3 cerium indium, everything all right here. If you look at this, you have cerium in the pore, indium in the pore, and outside, aluminum and oxygen. This is the alumina outside the pores. Everything worked fine. It's cubic, but then we start to characterize these materials. Here's what we found for susceptibility. As we observed for gadolinium indium-3, here we also saw this huge suppression if you compare nanowires and bulk. So it was like 10 Kelvin, went down to 2.4 Kelvin. But now if you look at the moment we analyzed, Key-Vise model is not so far from the cerium 3+, so everything working just fine. And when we analyzed the Key-Vise temperature as opposed to this Niel temperature, what we found is always a larger Key-Vise temperature compared to Tineo for both bulk and nanowires. This indicates the presence of some magnetic frustration there. And if you compare the ratio between Key-Vise temperature and Tineo, it's more pronounced for the nanowires. It's greater for the nanowires, indicating a frustration or more pronounced frustration for the nanowires. So let's look at the specific heat data right now. Again, clear suppression of this transition. It is, the peak is a little bigger. That has to do with the alumina template over there, because we have to measure everything together. But what's important here is the suppression of this temperature. This is really drastic change. And when we apply field, let me see, oops, it didn't work. What I was supposed to show here, what we see is this dependence with field, the peak shifts and broadens, it eventually shows a double picture, a double peak feature here. That was observed before for some sort of disordered or frustrated materials in 115s, and indicates a field-induced phase transition or a short-range correlation in these guys. These are macroscopic characterization of this system, but our red gives us some clue about what is going on with these interactions. I don't see the shade that I put there, but if you analyze the entropy at the transition, we can see that it's not recovering the full entropy here for the doublet here. It's halfway, it's only 0.5, indicating a very strong suppression of the crystal field. Okay, well, let me go faster here. But also the suppression of TNAO shows that RKQY is being suppressed, which may be favoring Kondo interaction. Let me show you now the characterization we did using NMR. This is a microscopic, a local technique, so we could look into detail in these guys. But I would like just to show you how we see the spectrum, so you can understand what we found there. In indium, we look at the indium nuclei. Indium is 9/2 with 9 transitions, split by the quadrupole interactions, so it's very complicated to look at. And the Hamiltonian, nuclear Hamiltonian, is Zeeman plus hyperfine. We combine in this way, so here we have the quantity of, we call night shift. And the second term is the quadrupole Hamiltonian. So we should expect this sort of result here. If you don't apply magnetic field, you do zero field NMR, or some people call NQR, we should observe only 4 transitions. It's degenerate here. But if we apply field larger than the quadrupole, and then we break the degeneracy, and we should see this very large 9 transitions spectrum here. So what happens when we look at the bulk material, beautiful 4 transitions, like I mentioned here, this is NQR, and before and below the TNAO, here's the ordered state. We can get this sort of result and calculate, diagonalize all this matrix and calculate the ordered moment about 5.5 kilo-Oersted at 4 Kelvin. But we couldn't see the same results, NQR results for the wire. That was puzzling us because we didn't know at that time this quadrupole effect was being suppressed just because now we had this different morphology. So we were kind of frustrated, but then we went to Tallahassee High Field Lab and we said, well, there's nothing they cannot confess if we don't apply field enough or you go down in temperature enough to see what's going on there. So we went there, measured this in very low temperature, below 2. And what we see here, here's the copper signal from the solenoid, the RF coil. Here's the aluminum signal from the alumina template. And with a very, very good faith here, our indium spectra is here. That's kind of frustrating because the signal is very weak. The density of wires inside of the template is low, but we could see some signal. We can fit it and explain, as I'm going to say real quick here. So to understand that, we try to model it, calculate, diagonalize exact diagonalization with the Hamiltonian and explain. Well, the first guess was using the quadrupole frequency from the bulk material. And as you can see here, those are the frequencies for that. And it doesn't match, those lines do not match our spectra. So this doesn't work for our nanowires. So the green lines here now match what our spectrum displays for each position line. These are the new frequencies, but we had to consider different parameters in these calculations. I'm going to explain later. But the first important result here is that nu Q changed from 9, almost 10, down to 1.8. This is a drastic suppression of crystal field, which was actually suggested by the analysis of the entropy from the specific heat. Now we could prove that, actually shrink our spectrum here. So, and also because we had to change the parameters here to explain the spectrum, we had to allow these Euler angles in plane. It kind of gives us some suggestion that our nanowire is not 100% single crystalline, not yet. We have to improve this. But other than this result, we had a very important result already here. So if we track that going down in temperature, what we found is, again, the transition was suppressed. I'm sorry, it's not appearing here. There's a mark here in the same temperature for 5 Tesla, where we measured the spectrum, and we saw that this has this suppression of TNAO from NMR as well. And when we compare the energy scales here, magnetic and the crystal field scales, it kind of match really well if you compare bulk and nanowires. So there's a proportionality here. So again, even NMR, a local probe, could also give some hints about, and is very consistent with the results. We did some EDS, very specialized EDS, manipulate this template to measure what's going on with the wire inside of the nanopore. So we did EDS locally here. We confirmed the lattice spacing, the lattice parameter, which remains cubic. That's fine, at least at room temperature. However, when we cool down, However, when we measure this at the nanowire there, these are the pictures. This was the pattern for the single crystal. And despite these spots here in higher reflections, we saw just a very circular pattern here indicates again, and further corroborating with NMR, that this is not 100% crystalline, single crystalline. All right, with that I come to my summary of results. I'm not gonna repeat all I already mentioned, but I would like to leave here the message that this is a work in progress. We are still improving the nanowire quality. But what's important here is that we can map what's going on with the underlying physics in these materials just by changing morphology. So RKKY was suppressed, Kondo in principle was favored here, and crystal field effects also suppressed. So this work is just put there in archive with if you are interested. I would just like to thank the organizers again. Eric, Rui, Daniel, Rafael, Eduardo, and Thais, thank you very much. And thanks for your attention. I'm glad to answer questions too. Agora
Okay.
você assistiu.
So, Ricardo, thanks for the nice talk.
Thanks, Mark.
Having tried and failed to grow these nano crystals also with the group over there, I know how hard it
It's
is
really
to
hard.
actually get these things, and it's very nice to see that it's going well with the CeIn3. Two questions here. First of all, what do you think is the mechanism behind that suppression of the CEF? What did you say is the thickness of those nanowires in your case? You said 75 to 170. What was that? Nanometers?
Nanometers. No, yeah, nanometers.
Nanometers.
That was the diameter of the nanopore. 75, the minimum. You can choose. The one was about 100 something. 150, I guess, marks.
So what do you consider to be the reason for the suppression of CF in this case?
Suppression of?
The CEF, the
the crystal field. Yeah, that's something we wish we could have, actually, this kind of analysis at low temperatures, like EDS or so, this FIB, but so far we can only look at that in a room temperature. But I think the lattice spacing is changing. That one is just room temperature. So it remains cubic and everything at room temperature. So I kind of guess, because the material is inside of the pore, it might be suffering some sort of pressure when you cool down. So we went down to millikelvin. Because the fact is similar. It is cubic. It's still way cubic down there, but a small change is very sensitive, actually, especially what we call crystal field. The electric field gradient is really sensitive to any change.
But you're measuring, when you cool down to lower temperatures, you're cooling everything, right? The alumina template
everything
together. So you're thinking that from differential dilatation effect, you might
That's
have
a guess. We don't know.
Okay.
But it's the simplest answer to you right now. Is if there is some sort of pressure over there in a special direction, you are changing, maybe it's becoming distorted a little bit, but like Edu said, it's still cubic because we can see the signal, we can calculate everything using the symmetry there. However, I should mention that it's only possible to see the quadrupole splitting because the punctual symmetry at this indium site is not cubic. So if it's distorted, you wouldn't see. But that's enough already to break, the symmetry, the high symmetry, so then you can see electric field gradient, the quadrupole effect, in other words. The punctual symmetry may not be cubic, or actually is not cubic, because we see the quadrupole splitting. But the material or crystal structure is still cubic.
And what about to improve that crystalline quality that you showed?
Well,
didn't you try the annealing? I mean, the first thing that you might try to do that is just anneal the whole thing and see if it improves, right?
Yeah. Well, here's one point. The way you control the size of the pore is doing some etching, acid or etching or something. So if you look at here, see the pore is not so smooth. So one thing I suggested for them to try is to make some sort of sputtering, gold or titanium or something, and make some metallic film over these pores. And then you use the technique again. The other one is you grow sample, is cycling the cool down, the quenching, going up and down the temperature so you can nucleate better. So these are things that they're going to try, I guess, they're going to try in the future. But yeah, over here, actually, they were trying to enlarge the pore. That's why we destroyed the template, because, like you said, it took we grew these nanowires once 5 years ago, and we never repeated, right? You know that. CeIn3 is really hard. So then they were trying to enlarge the nanopore to facilitate that, maybe to grow easier. But there's no need for that. Actually, we should keep the template. We should keep the templates with smaller nanopores. But to ensure that the flux, the metallic flux goes in, I suggest to make this film over that. We don't know if it's gonna work.
More questions? Sorry.
Ricardo, in your heat capacity curves, you first show us a heat capacity curve, and you said, okay, this one is a little bit higher because it kind of includes the contributions from the aluminum templates, right?
Yeah.
And later you show us a comparison of your an evaluation of the entropy. The next slide you show an evaluation of entropy, right? No, not this one.
This
the
one?
one with the entropy.
Oh.
Yeah. Sorry.
This one, yeah.
So, and you're like comparing this one with log 2, right? So.
Yeah, log 2
did you
because the ground
somehow-
state's doublet. It's a
Yeah,
gamma
but-
7.
But did you somehow get a subtraction, and or I mean, how did you do it?
They're doing this. I asked them before this talk. I said I want to know the gamma, and Pascal and Elena are doing the best they can right now. There's shock anomaly here. There is magnetic contribution that we don't have the reference component to also subtract here. So what they're doing is try to estimate the area below this peak and compensate somehow. And the number they gave me was 500. You know, the pure one is 130. The bulk one is 130. They are estimating 400, 500 with a large error because of this contribution. Not only the template, but other things that are also there. And we cannot subtract right now.
Okay.
It's hard to analyze this.
Okay. Thank you. So, in principle, this comparison.
Yeah, we should grow lanthanum indium 3 or lutetium or something and measure and subtract, and then we are talking, I guess, right?
Oh, yeah. Yeah.
Yttrium, maybe.
Okay.
Sorry, I don't have the answer. But yeah.
All right, with that, let's thank the speaker.
Thank you very much.